The reality twin is a small-scale model of an electrical distribution grid, coupled with the Bifrost simulation to provide energy system data and an environment for our OpenSwarm DDA nodes. Let's add an element like a generation device, like this wind turbine, to our canvas here in reality. And we see that this wind turbine registers itself into the Bifrost simulation. When I now start the simulation, we can see in this chart that this wind turbine has a certain infeed potential, in our case now almost 22 kilowatts, but nobody can consume this energy because the wind turbine is not allowed to feed into the grid. To do this, the wind turbine has to be added to an energy community. This can be done by just rotating the element. We remove it from the canvas and turn it by 90 degrees, because each rotation by 90 degrees is an allocation to another community. In this case, it's community A. When we now start again the simulation, we see a Docker container is spawned. This is an DDA agent which tries to find another one in his community. Let's have a look. We see here that the DDA has information about his node, for example, what is the current production, also about who is else there, but he cannot find any demand to fulfill the production. To overcome this, we have, of course, to extend our community. And for this, we use, for example, this charging station. I also take the charging station and put it in a certain direction to add it to community A. Let's start the simulation again. We see now two nodes are spawned, one for the EV charger and one for the wind turbine. Let's have a look. For example, this is the charger. This charger is just telling the community that he has no demand currently. So let's add a car, like this blue one, to the charging station, which will initiate a charging process, which can be observed on the one hand at the log of the node and also of the output power. And what we also can see is that the wind turbine now meets the demand of the charging station, but there's still more demand. It could produce more power for a later usage. Maybe we add another element, in this case a storage system. These are these elements. Place it here, right beneath. Charging station. We can change the storage size by adding these elements to the system. So let's start again the simulation. We see another DDA node spawned. This is the storage system. It provides the information about how much charging and discharging power is available depending on its SoC. And we see now that when the control algorithm is working, that all power generated by the wind turbine is used to once charge the electric cars and second charge the battery system. You can also observe the change of stage of charge with the lights. I can also configure the size of the storage system in terms of removing capacity, so now the storage system is full, and we see instantly the wind turbine has to adjust its power. When we remove, for example, the generation now, for example by removing the wind speed, so no wind is blowing anymore, we see that instantly the storage can take over, provides power to the charging station, and when we add another car, so we increase the charging power. We can also observe how the storage is drained by the system to provide still enough power to the community. Let's rearrange a little bit here our system. So I allocate the wind turbine now to community C to give our existing community also the possibility to generate power. We add, for example, here this solar panel, solar farm, this generation plant. This one can also be configured by these elements by adding solar panels. I can also add infeed power to the system, and now we also add another load in form of this charging station, and to have an initial state we move our cars from the initial one. So we have now two communities in operation, Community A and Community C. Now let's observe what is going on when I start the simulation. So we see, for example, when I add car to Community A, the demand is going up, and this one is met currently by the PV farm, solar farm. The rest of the demand is supplied by the storage system, and when sufficient PV production is present, also the storage system gets charged again. So I move this up here. So let's have a look now at the wind turbine, Community C. I add a car to the charging station there. And now we see that the charging power is provided now again by the wind turbine. Let's add another car, like this red one. And what we can now observe is there's an increase in charging demand, but the wind turbine, despite it has full potential to supply this charging demand, cannot provide more power. To answer this, we have to look at new components in our system, the so-called grid sensors. These grid sensors are also DDA nodes incorporated in a swarm. This swarm is operated by the distribution system operator in form of intelligent measurement devices installed, for example, here at the beginning of our feeder lines, where, for example, the wind turbine is installed. The sensor nodes have the task to observe the power over the asset, for example a cable, and ensure that certain grid limitations like a power limit are kept. How is this done? In our case, the DDA nodes of the energy community propose their operation in terms of power distribution to the sensor nodes. The sensor nodes use this information along with a primitive topological information to check if certain grid limits are violated. If this is the case, this information is fed back to the energy communities so they can adjust their operation. In our case, sensor 1 ensures that not more than 10 kilowatts are transported over his cable. This is done completely without any external configuration. Only the swarm intelligence ensures that the energy community swarms and the DSO swarm in form of the grid sensors is active. When a car is removed in community C, the charging station needs less power. Therefore, the community comes back to its normal operation without any limitation through the grid sensors, as no power limit is exceeded. When a car is added again and community C would exceed the power limit, again we can observe in the log that this information is processed and the grid sensor node ensures that the power limit is kept. Let's extend our model now again by, for example, these households which provide over the PV system also power to energy communities. Let's add here, for example, these two houses and add them to community B. Also add a charging station to community B. So we have now total 3 energy communities operating on 2 feeders. Let's start the simulation again. So what is happening when we add cars to the newly added charging station of community B? What we can observe is interestingly that obviously the wind power plant, which is member of community C, can now feed in more power. How is this possible? This is because we have 2 load flows happening now. Like we have a generation here and demand here at this feeder. So this is going over sensor 1 and sensor 2, so sensor 1 and sensor 2. But we have also now feed in here from this side over sensor 2 to sensor 1 and to this charging station. So the controller can now see there is a cancellation in load flows. So in physics, the generated energy from the wind power plant is providing also the charging station, and the sensor limit is still kept. In this way, without telling anything to the overall system in terms of a global topology information, the system can recognize that there's a more optimal way to operate. When I remove, for example, now the charging power again, then the wind turbine has to reduce its feed in, the controller to provide sensor, the sensor limit instantly switches off the wind power and allows again to feed in the 10 kilowatts. Add again the charging power to the system. The more can provide it. And I think this is one of the big advantages in our OpenSwarm realization in PoC1, where without any need for external configuration, the nodes themselves, based on their control strategy formulated with Natural 2 in form of standard control theory, state machines, the nodes themselves can decide how to operate and keep all limits at all time